Let's look at roots and multiplicity in polynomial functions. Right? Multiplicity means the number of times a factor is repeated. So if I have a function, let's call it g of x, and it's in factored form, and I have x and x minus 3 squared and x plus 2 to the fourth. This squared right here and this to the fourth are telling me that this parenthesis is going to be written out twice, x minus 3, x minus 3, and this to the fourth is telling me that this x plus 2 is going to be written out 4 times. We say that that factor is repeated 4 times, or that it has a multiplicity of 4. This x has no exponent, or it has a secret exponent of 1 is a better way of saying it, I guess, and so that is only repeated once. So we say that this factor of x has a multiplicity of 1. And usually if there's a multiplicity of 1, you don't say it has a multiplicity. It's just understood. X minus 3 squared has a multiplicity of 2. And x plus 2 to the fourth has a multiplicity of 4. Okay, so the exponent of any given factor is referred to as its multiplicity. Okay, a root or a 0 is the value of x that makes that function equal 0. So if I'm finding the roots of each function, I'm saying which values of x make my function equal 0. So remember when we were dealing in quadratics, we would set this equal to 0, and then we would use the 0 product property. Which values of x are going to cause this to be 0? And in this function here, I have several equations that will help me solve that, or answer that question. So this 3 right here, there's nothing I can do to make that 3 equal 0. Can x minus 7 equal 0? Sure it can. If x minus 7 equals 0, then x has to be 7. So my first solution, or my first root, is 7. Can x plus 3 equal 0? Sure it can. So x is negative 3. Oops, let's put the negative though. Negative 3. So negative 3 is a root of this function. Can x plus 1 equal 0? Sure it can, and that value that makes it equal 0 is a negative 1. So we say that this function right here has 3 roots, 3 zeros, 3 solutions. Those are 3 ways of describing the same thing. 7, negative 3, and negative 1 all make this function equal 0. Okay, if I'm looking at this, I have 2 things that can make this function equal 0. Either 5x squared equals 0, or 3x plus 10 equals 0. If 5x squared equals 0, then x has to equal 0. 3x plus 10 equals 0, then x has to equal negative 10 thirds if I solve that equation out. All right, so let's connect the roots and the multiplicity. Let's see how they all connect to the graph. So if I'm looking at this function f of x and I want to know the degree, well, I'm going to say this is in factored form. And if it's in factored form, I have to add up all the exponents. So this has an exponent of 1. This has an exponent of 2, and this has an exponent of 3. So the degree of this polynomial is going to be 6. All right. The roots of this polynomial are the values that make each parenthesis or each factor equal 0. So if I want to look for the roots of this polynomial, I'm going to say, well, what makes this first parenthesis 0? That's a negative 3. What makes this second parenthesis or this second factor 0? That's 2. And this third one is going to be negative 1. So the roots of this are, negative 3, 2, and negative 1. Well, you can see that right on this graph. I've got negative 3 right here, negative 1, and 2. Whatever values make my polynomial equal 0 are going to be the places where we cross the x-axis. These are my x-intercepts. Now, if I'm looking at this same graph, I want to be able to describe these roots. Each one of these roots looks a little bit different on this graph. If I'm looking at the root at negative 3, so right here, all right, Do you see how the line of this graph just goes straight through at that root? There's nothing weird happening. It just crosses right through at that root. So when I describe it, these are words that I use. I say it goes straight through. Okay. But that's a little bit different than what happens at -1. At -1, if you're following the graph, it flattens out. It makes what I call a schwump. This is very important that you spell it correctly. Schwump. I'm just kidding. That's not a real word. But that's what it does. It levels off and then it continues on its way. Okay, so it flattens out. It makes a schwump. The third root that we're looking at is this 2 right here. All right, and what this graph does is it comes and it touches the x-axis at 2 and then it bounces right back up. So the informal way of describing this, I will often refer to it, is a bounce. The formal way of talking about it, many books will refer to it as tangent to the x-axis. And tangent is a word that means touches at one point. So this is tangent to the x-axis. Okay. When you're looking at this graph, you're going to say, well, is the graph going straight through? Is it schwumping? Is it bouncing? Okay, and the way you can know that is the multiplicity of the factors. So if I'm looking at each one of these factors, x plus 3 has a multiplicity of 1. It's only repeated once. And that means that at that root, that -3, whatever makes that factor 0, okay, that's just going to go straight through. Multiplicity of 1 goes straight through. X minus 2 has a multiplicity of 2. It has an even numbered multiplicity. And anything that's even numbered is going to bounce or be tangent at that root. So at the value that makes that factor 0, which is 2, okay, that 2 has a multiplicity of 2, which means that it will bounce. That's its multiplicity, and that determines its shape. It determines its behavior at that root. This last one has a multiplicity of 3. At the root of this is a -1, because that's what makes it 0. And at that root, you can see that that multiplicity of 3 causes it to level off there. That's your schwump. So that multiplicity of 3 creates a schwump. As a rule, odd multiplicities go through, even multiplicities bounce. Okay, so let's look at this. And I'm going to say, well, I have 3 roots here. I have this one here, I have this one here, and I have this one here. At this first root on the left, this root of -3, okay, I said -3, but I wrote -1. Why did I do that? This root is a -3, okay, and you see that you're coming down, you're leveling off, and then you keep going down. So we're going to say that that has an odd multiplicity. This root of +1, where x is +1, I'm coming up, I hit the root, and then I bounce back down. I'm tangent at that point. So that must mean I have an even multiplicity. And at this last root, where x equals 2, I go straight through. So that must mean I have a multiplicity of 1. Okay? Odd multiplicities pass through. Even multiplicities bounce. And if you just go straight through with nothing interesting happening, then you have a multiplicity of 1.